Lecture 12, part 2. So we're going to go into the mathematics behind how to solve for PCA. So in the previous part, we talked about what is PCA. So basically, we have a bunch of data points like this. We want to first find the direction that captures the greatest variation, and then we want to keep doing this and find the next one. So before I actually go through the algorithm, we need a lot of linear algebra and statistics. So let's start with the basic ones first. So the first concept is a unit vector. So unit vector is basically a vector with length 1. So it's basically, this is a length. Note that they are not actually equal to that. So that's not always equal. This thing squared is always equal to the dot product. So don't be confused. That is not the definition of the norm. The norm square is that, but since the norm is 1, they're basically the same thing. So basically, if the dot product between a vector and itself is 1, then it's a unit vector. So that's the first thing. And the second thing is two vectors are orthogonal or uncorrelated. Usually we call them perpendicular in a geometric sense, but in general they are orthogonal in any vector space. But in any case, if the dot product is 0, so dot product, we usually write the dot product as one vector transpose multiplied by the other vector. We have done this like many times already, so just remember this as a definition of two vectors being orthogonal. So like this, perpendicular. And the next concept is projection. So if you have a vector and you have another vector that goes in another direction, the projection of that other vector onto our u vector is basically just like regular projection. And it's basically finding the vector along the UK direction that's kind of closest in distance, in perpendicular distance to the original vector. So if you look at this vector here, the distance is longer and that one is longer as well. So there's only one. That one is called the projection UK of x1. So definition of projection can be actually extended very easily to higher dimensional spaces. So for example, you have u1 and u2, and if you want to project a vector xi here onto this, say, the drawing space, then you're just projecting it like casting a shadow, and that vector here, that's our projection onto u1, u2 of xi. So because it's not often used here for PCA, so I will not talk about this and the formula for this, but basically if there's only one of them, then the formula is this. So this is kind of the definition. And then, given the definition, we know that these u's are unit vectors, so we know that this u transpose u is 1 because they are unit. Then we can get rid of this, and then we're left with that expression here. So again, this is our general formula, and this is just for unit vector projection. And the next is the length of the projection is literally just the length of the projection, and it's the length of this expression here. And this length, note that this thing is a scalar. Right? So this thing is a single number because it's a dot product between two vectors. So it's like a constant. We can factor it, not factor it out, just put it outside of the norm. And then the norm of this UK, since it's a unit vector, is 1. So it basically, we're only left with this scalar, and this scalar represents the length of the projection. So that's another formula to remember. And next, let's move on to statistics from linear algebra. So we're going to write the data matrix slightly differently. So usually each data point is a vector, so they are like vertical vectors, and we write the data matrix like that. But I remember in P1, P2, and say P3, you roll the instances like one row anyways. So that's basically what we're doing here. So each row here is one instance. And that's our x11, x12 until x1m. And m is the number of features. So that's how we are going to write down this data matrix. So it's slightly different from the standard notation, but it's the same thing. Okay, so the next one is the mean. So this mu here is the mean, and it's just the regular average. Just sum up these vectors. Each one of these vectors is n by 1, and you sum them up, and divided by n is still a n by 1 vector. Okay, so I should know that these vectors are still vectors, so technically I should have transposes on these. I'll fix it in the lecture slide that I post. Okay, in any case, let's move on to the variance. This sigma thing is our variance, and usually in statistics it's called variance covariance matrix, and here we're just going to call it variance. And it contains elements that are actual variances, but let's talk about that later. So as how we usually compute variance, it's just every data point subtract the mean and kind of square it. So this thing kind of looks like a square, and then just sum them up, and they've divided by the total number of data points minus 1. So that's the standard definition of variance, which is the same thing here. But note that the product, the way we are taking the product is kind of different. It's something transpose. Usually the dot product is something transpose something. So here it's done intentionally, it's not a typo. So here each one of this is n by 1, and these are 1 by m if we transpose them. And then if we take the product, it becomes an m by m matrix, and we are adding up n m by m matrices. So this whole thing, this variance, that's why it's called variance covariance matrix. It's not a single number, it's a matrix of size m by m, the number of features multiplied by the number of features. So let's actually spend some time to look at how this product's done. So remember, regularly when we multiply two matrices, we do one row multiplied by one column, one row multiplied by one column, and then we basically keep doing this, and then we get another matrix. And here we're going to do the same thing, except for the first one is an n by 1 vector, n by 1 matrix basically, and the second one is a 1 by m matrix. So the first row multiplied by the first column, you just get one single number. And then the second row multiplied by the first column, you could just get the second number. And similarly, you can do the first row multiplied by the second column. First number multiplied by the second number, you get that one. And basically, if you keep doing that, you'll generate a bunch of points that form a matrix. And each element is just one number multiplied by another number. And then you have this lots and lots of n by n matrices for each data point, and you just add them up. So that's the variance covariance matrix. It's not sum of a bunch of numbers. This is not dot product. Okay, so let's move on to the next thing. So we want the expression to be simpler. We don't want to write this minus mu every time. So maybe we should just subtract mu to begin with. Then we don't have that. So what we are doing here is basically we define an xi prime, and then we are doing xi primes using xi primes here, and our x here is no longer the original x, it's just the x with the means subtracted already. So these x's are the instances with zero mean. So these are instances. Let me actually write it down. With mu is exactly 0. Okay, so let's actually look at how, why these things are the same. So we talked about this part already. It's just one vertical, it's not called vertical vector, sorry. It's a column vector and one row vector. So I'll call these column vectors vertical vectors and these row vectors horizontal vectors anyways. So we have one element multiplied, first element multiplied by the first element. Then we get our first element here. So it's the product of these two, but then we're adding up over different I. So I is 1 until m. So remember how we get the first one. And let's see what's happening here. So here we have our x transpose. So our x looks like this. Remember, like 2 slides ago, we talked about this is our x1, this is our x2, where we're putting the instances as rows of the matrix. So the transpose will have this standard version with instances as columns. And what we're doing here is not actually multiplying them correctly. We're doing this row multiplied by this column. And what is that? This is the first element of the first instance multiplied by the first element of the first instance. And then the second one multiplied by the second one. Third one multiplied by the third one. The first element of the second instance multiplied by the first element of the second instance, and so on. So it's exactly the same as this idea here. We're just adding them up. Here we're adding them up as well. So the dot product of this row and this column is also the same. So probably you can try it yourself. You can try it with a small matrix if you want, if this is not clear. And or you can try something like A, B, C, D and actually see that these two expressions are the same. Let me actually do another one. So suppose we want this one here, then it's the second row multiplied by the first row here. So the second element of each vector multiplied by the first element of the same vector. And we add them up over different instances. And let's see, what's this one here? This one is the second row multiplied by the first column. So again, it's the same. It's the second element of the first instance multiplied by the first element of the first instance. And then again, second element of the second instance multiplied by the first element of the second instance, and so on. So these things multiply to that element as well. So that's why these two things are the same. We will use this identity later again. So that's how we simplify a bunch of like the sum with a lot of vectors into just the product of two matrices. Okay, so let's move on to do more algebra. So here, as I said, usually it's called, in statistics, it's called variance covariance matrix. And here the variance are the ones on the diagonal. So here we have a matrix that's called sigma, and these things are variances, and the other ones are called covariances. But we're just called the whole thing the variance. But in any case, the covariance between, say, the same feature and the same feature is called variance, if you want to remember it that way as well. That's okay as well. And here is sigma 1, sigma 2. So it's the variance of the first feature, variance of second feature, and so on. So again, it's the jj's element of this matrix, and usually it is written in this form. It's xij minus mu j and square, because this thing is by definition 0, because we normalize these instances already to have a mean 0. That's why we don't need these things. We just have each element square and then sum them up. So that's basically just confirming our regular one-dimensional variance formula is still correct. However, we don't want to write this. This is a sum of something that looks not so nice. We will rewrite it as a vector multiplied by a matrix and then multiplied by a vector. So if you know what I'm talking about, is EJ transpose sigma. This sigma is not the sum, it's just the variance matrix, and EJ. So EJ here is a vector with all zeros with only one at the j's position. So let's actually take a look why this thing is equal to the j's element. So first transpose it. So lot of zeros and with the j's element being 1, and then we have our sigma matrix, and then we have lots of zeros with a 1 and here. So this is our EJ, sigma EJ. So first let's do this step. So again, row multiplied by column, row multiplied by column, row multiplied by column. And what do I get? So all of these are 0, so multiplied by anything is still 0, and we add them up, so we only 1 times this j's element is added up, so we only have that as a result. So the same thing goes to the second column and third column. So after this multiplication, it's basically we get a row. So EJ transpose sigma, this part is just row J. And then the next part, you can probably guess that would be our column J. And indeed it is. So everything else is multiplied by 0. Again, row multiplied by column. Everything is multiplied by 0 except for this j's element. So you do get this j's element here. And in particular, this is the j's column of the j's row. So this is indeed sigma jj. And that's our expression here. Okay, and this idea is used in the next slide. And what we're going to have is this variance element, which I said is sigma jj, is equal to the expression that we just derived, this EJ transpose sigma EJ. And then we can write this sigma hat, or I just call it sigma, it's x transpose x. So just put this in, remember there's a constant in front. And then we have an expression like this, purely in matrix form, as matrix multiplication of matrices. And we also know that these things are just the regular variances. So if you go back and look at this formula here, they are just the sum over each xij squared. And these each xij squared is just e times xi. So let's do it again. So with only 1 and xi, this is xi1 until xim. In particular, there is an xij here. When you multiply these two, you get 1 times this. So you only have this. So this thing is indeed just our xij. So we know that this thing is both equal to this part and also equal to this. That's why these two are equal. And the way I'm writing it down is not clear which two I want to show that they are equal. So I want to show that this thing is equal to this. And of course, we're just going to use that part is the simpler version. So the next thing we want to do is we want to do the projected variance in the same way. So by definition, the projected variance is this expression here. You just do the projection. So remember, that's the projection. The projection formula is this, but that's the length. Remember, that's the length of the projection. Here, the variance of the length of projection is basically this expression here. Again, it's the variance of the length of the projections. All right, so we start with this expression. We want to go back to there. Of course, there's going to be lots and lots of algebra, but I'm going to skip it, and I'm going to say that it looks like the relationship between this one and this one. So it's so the algebra is very complicated. Basically, I don't want to go through this, so I'll just say that they are similar. So using the equivalence between those two just that we just derived, I want to just say that these two are similar as well. So we can go back from this expression here, the variance of length of projection, back to the matrix expression like this. And this expression, by the way, is just that. Okay, so hopefully you are clear what we're doing here. We're just doing some kind of algebra to get an expression like this as our variance. Okay, so let's continue. Now we know that this is the variance of the length of the projection, basically what we call the projected variance. Is the variance of the length of the projection is this expression here. We want to maximize it by choosing a direction u, such that this u direction is a unit vector. So the bad news is when we talked about regularization, we didn't talk about Lagrange multiplier. So I don't really want to introduce it here. So let's just say that for some reason we can convert this constraint optimization problem to this this maximization problem here. So what we're doing is basically convert this constraint into lambda multiplied by the constraint, and then we get an expression like this. So somehow we're still skipping a lot of algebra. I apologize. So if you don't know what Lagrange multiplier is, if you want to learn it, it's good. If you don't, you can just remember that we can, when we maximize some function f with respect to g is, such that g has the constraint that g is equal to some constant c, then what we can do is this is equivalent to maximizing f minus lambda g, and by choosing lambda and the original variables, and that idea is called Lagrange multiplier. And I will skip the derivation here. Obviously, it's a very long derivation. So let's get back to here. Here now we can take the derivative and hopefully use maybe gradient descent. It turns out we don't need to, because when we take the derivative with respect to u, then we get just the coefficient is equal to this coefficient here. And if we straighten out the vector notations, then it becomes sigma u is lambda u. Okay, so at this point, you realize this is just the eigenvalue, right? So a matrix multiplied by a vector is the same as a constant multiplied by a vector. So you can figure out these two vectors and this constant by figuring out the eigenvalue and the eigenvectors. So this is our eigenvalue, and these UKs are our unit eigenvectors. Okay, so now we have most of the mathematics we need, and actually we can actually substitute this back into here. Let's actually do that. So here, this sigma u, remember the last condition here, sigma u is lambda u. So if we put lambda back here, you can, because lambda is a constant or a scalar, you can like push this out, and u transpose u again is a unit vector, so it's 1. So basically this expression here is just the projective variance. Lambda is this expression here, which is the projected variance. So the larger the lambda, the larger the projective variance. So what we want is the largest lambda one and the UK corresponding to the largest lambda. So what we'll do is we will list all of the eigenvalues and order them in the increasing order. So the largest one corresponds to U1, and this is our principal component, or the direction that captures the largest variation, number 1, and this is our principal component number 2. and so on. So that's what we are going to do. And again, there are some mathematical property like why this is always symmetric, positive, semi-definite, and so on. But basically, they guarantee that there exists these eigenvalues, and we can order them somehow, and then we have the corresponding eigenvectors. So that's basically all you need to know. And we're going to call these unit vectors the principal components. So in the next slide, I talked about how to actually compute these. I will not ask you to compute any of these things, so it's okay. You don't need to know that. If you want to implement it, don't implement it yourself. It takes a long time to implement any eigenvalue algorithms, so you should probably use a package. Most of the program language, they do have a package, linear algebra package that computes these eigenvalue and principal components. So I will skip this slide basically, and that's actually all I want to talk about PCA, the mathematics behind PCA. So the idea of finding these principal component is just find the largest eigenvalues of that sample variance covariance matrix, and then order them in the correct order, and then find the corresponding directions. Those are just the principal components. Okay, so and another thing I want to talk about here is how to choose the number of dimensions. So it's the same idea with the clustering, how to choose the number of clusters. Well, the same way is always, the first one is always using prior knowledge. So if we know how many principal components we want, or like a requirement, then we can just use that one. Not many people actually use non-zero eigenvalues because the number of non-zero eigenvalues are usually large. So we usually use all the eigenvalues that are larger than, say, 1. Or we can choose some arbitrary threshold. But again, this threshold will be arbitrary, and it depends on the prior knowledge.